Okay, so my name is Leah, and I'm a third year PhD student at NTNU, and I mainly work with Fully Homomorphic Encryption. And today I would like to present a paper, Practical q-IND-CPA-D Security for Approximate Homomorphic Encryption, which is joint work with Jean-Philippe Bossuat, Ana Maria Costache, Christian Mouchet, and Juan Ramon Troncoso Pastorida. And so a small overview of the talk. First, I would like to introduce what noise is in FHE. You're probably all familiar with the general problem of noise in FHE, but since it's very important for this particular topic, I would like to talk a little bit more about it. Then introduce approximate homomorphic encryption and the Li and Micciancio attack on CKKS and the security notion that resulted thereof. And lastly, how to achieve CPA-D security for CKKS. Now, this paper lives a little bit in a niche of FHE world, which is why these all are the preliminaries, and this actually is the only thing we do in the paper. So please bear with me while I go through all the preliminaries. And so I would like to directly start with what is noise in FHE. Now, most FHE schemes today are lattice-based, so usually we encode a message as some dot, like for example, the golden dot down there. And then we pick a public matrix A and a secret vector S and add to M the matrix A times the secret vector S. And this gives us some other lattice point, like the one the blue arrow points at. And then for extra security, usually we add some small error E. And now to go back down to the message, what happens is we need to find the nearest lattice point, and then we can just reverse the operation of adding the A times S. Now assume we've got a second message, M prime, that again we encrypt in the same way. And now we add those 2 points, then already we see while after adding E and E prime, we were still fairly close to lattice points. If we add those 2 points, of course, we also add E plus E prime, and we move much farther away from the closest lattice point. That is, the error grows, and eventually the closest lattice point will be one that is different from the one that we originally wanted, and decrypting will lead to a different message than one that's actually encrypted. So this leads us to what I took the liberty of calling the FHE noise dilemma. We need the noise in FHE, because if we don't have the noise is what guarantees essentially the security of the scheme. If we don't have the noise, then the scheme is insecure. But if we have too much noise, eventually we will not be able to decrypt correctly. So to know whether we still can decrypt correctly, we need to know exactly how much noise the ciphertext has. But if we know exactly how much noise the ciphertext has, then we can subtract it, and then the scheme is no longer secure. So we need the noise for security, but it hinders correctness. And for correctness, we should know as closely as possible how big the noise is, but that, on the other hand, hinders security. So since this problem with the noise has been around since the very first FHE scheme, of course, there are different ways of dealing with the noise in FHE. So, for example, in BGV, the randomness that gets added, this E, gets multiplied by the plaintext modulus, and then during decryption, it gets a modular operation modular the plaintext modulus is performed, and the noise gets removed. In BFV, the meshes are scaled so that the noise in comparison is fairly small, and then during decryption can be rounded off deterministically. So to look at this a little bit in formulas, this is what a BGV ciphertext looks like. And then we can see, okay, again, as we saw in our image with the lattice before, we have the message, we have a public element that we multiply by a secret element, and then we have the noise, and the noise is multiplied by this T, and the T is the plaintext modulus. And then during decryption, we get some expression, which is this M plus TE modulo Q modulo T. And so then we see, okay, if we take this modulo T, then the noise will vanish and we just get the M back. The only problem is we've got this modulo Q before. So if our noise term gets much bigger or gets bigger than the Q, then we get a wraparound and we won't be able to recover the message. In a similar way, in BFV, the noise removal works in some different way. So here we see we've got a scaling factor in front of our message, but otherwise the structure is the same. And we don't have that the noise is multiplied by the plaintext modulus. So we just have the noise here. And then if we decrypt, we multiply again by the scaling factor, and then we can easily see that if the inverse of the scaling factor times the noise is smaller than 1/2, then this will round off and we again recover the correct message. But so when I explained those, how the noise gets removed, we always saw there are some conditions. So in the case of BGB, we can't have a wraparound modular the plaintext or modular the ciphertext modulus, and in BFV we need to make sure that the whole thing is smaller than 1/2. And so these conditions need to be observed and require careful bounds on the noise, and this also takes a toll on efficiency. So this is where approximate homomorphic encryption takes a completely new approach. The only today known approximate homomorphic encryption scheme, CKKS, was proposed at Eurocrypt 2017 by John, Kim, and Song. And it has a very different way of dealing with the noise than BGB and BFV. A very simple one, which is it just lets it be. So in the paper, the authors proposed Heian homomorphic encryption for arithmetic on approximate numbers, which today is more commonly called CKKS after its authors. And it is based on the BGB scheme, but it has a different message space. So here now the message space is no longer integers modular plaintext modulus, but the real order complex numbers, which means there now is no plaintext modulus by which the noise could get multiplied. Therefore, performing a modulus reduction modular plaintext modulus will no longer remove that noise. So what happens instead? The author showed that the randomness in CKKS does not grow as fast as in other schemes, and that therefore it can be completely okay to just leave it. And to, instead of returning a completely correct decryption of the message, to return the message plus some small noise. So this is where the name approximate homomorphic encryption comes from. Encryption has become approximate in that sense that if we take a message, we encrypt it, and we directly decrypt it afterwards, the message and a decrypted message won't be exactly the same. They will be quite close to one another, but they won't be exactly the same. And the authors argued that this is fine because if, for example, in machine learning, we use real-world data that is approximate in nature, and therefore, if you have then some small additional approximation due to the encryption-decryption, that also shouldn't hurt too much. So to show it in formulas, to make it a little bit more clear. So this is what a secret key CKKS ciphertext looks like. So again, we observe the same structure that we already had in the animation before with the general noise and lattices. So we have some plaintext, we have a public element A, we have a secret element S, and we have some noise. And now during decryption, we again decrypt in the same way. So we take the scalar product between the ciphertext and 1, the secret key. And then we obtain the plaintext plus A times S plus the noise minus A times S. And so this is the same thing as the plaintext plus the noise. Now, this is the moment where in BGB and BFV, some sort of noise removal was triggered. But in CKKS, now the E just stays there, no noise removal whatsoever happens, and the error is now simply considered a part of the plaintext. And we just return the plaintext plus the noise. So this directly leads over to the Li and Micciancio attack on CKKS. Now, CKKS in the original paper has been proven in CPA-Secure. And usually in CPA is the standard version of security used in FHE. Because we can't get in CCA2 security. Right now, there are some works on how to achieve in CCA1 security, but which is why for the time being, like IND-CPA is the security notion that is being used. But IND-CPA as a security notion has been developed for what I would call classical encryption schemes. So encryption schemes where no operations on the ciphertext are being performed, but where just this messages are get encrypted and decrypted and nothing more. So there has been suspicion for some time that for approximate schemes as CKKS, IND-CPA security might not fully cover what a passive adversary can do, because these schemes are quite different from classical encryption schemes. And this suspicion has been confirmed by a passive key recovery attack on CKKS, which has been presented by Li and Micciancio at Eurocrypt 2022. So I would quickly like to outline the attack based on secret key CKKS, since there it's much plainer what's happening, but it can equally as well be adapted to public key CKKS. Now we recall if we have a secret key encryption of 0, then our ciphertext looks like this. So we just have the public element times the secret element plus the noise. And the second component is just minus the public element. And now we can see if we decrypt this, an encryption of 0, the decryption is just going to return to us the noise. So if now from the first component of the ciphertext, which is public, which is A plus E, we subtract the decryption of that same ciphertext, which is just E, we'll just be left with A times S. Now, A is a public element. In the ring, it has an inverse with a high probability. So from A times S, we can just multiply this with the publicly computable inverse of A, and we'll get the secret key. And this is generally not good. But we also see that for exact schemes, this attack should not work, because there decryption simply returns the message, which is 0, which is already known to the attacker, so the attacker doesn't really learn anything more. So for exact schemes and exact schemes that correctly return the message that was encrypted, the attack has no meaning. But for approximate homomorphic encryption schemes, this is completely different, because here the decryption returns more information than just the message. Because in addition to the message, which might be known to the attacker also learns the error term. And we had already before, when we looked at what generally noise is in FHE, that we do need the noise for security. So we already see here that learning the noise probably will be very bad for security. And this is indeed what the Li and Micciancio attack shows. But this is not something that is captured by the IND-CPA notion. So CKKS does stay IND-CPA secure, even though there is this passive key recovery attack. So this is why Li and Micciancio proposed in the original paper a new security notion, IND-CPA-D, which they argue to be more adapted to the special case of approximate homomorphic encryption. So what is this IND-CPA-D security? Now, in the usual IND-CPA game, what happens? We have the game that generates the keys, the secret key, the public key, and in FHE world, also the evaluation key. And it chooses a secret bit B. Now it sends the public key over to the adversary, and the adversary sees the public key, picks 2 messages, MO and M1, and sends them to the game. Now the game encrypts according to the secret bit B, MB, as a ciphertext, sends this to the adversary. The adversary has a long look at this one, and then either decides to pick 2 new messages, MO and M1, or to make a guess for the secret bit B, and then sends the secret bit B to the game. And the game returns yes if what the adversary guessed was correct, and it returns no else. And we call a game IND-CPA secure if the adversary has not a chance of guessing the secret bit B with a probability bigger than 1/2. Because it always can, since there are only 2 possibilities for B, it can always guess B with probability 1/2. but we say it has a non-negligible advantage if its probability of guessing B is much bigger. Now, in the q-IND-CPA-D game, we still have the original NCPA game, so the adversary can do all the things that it was able to do in the NCPA game, but it is also allowed to do some more things. So, for example, it can pick from the state cipher and ciphertext, and from the state because the ciphertext need to be honestly generated, and it can choose a circuit C. Now it can send the ciphertext and circuit to the q-IND-CPA-D game, and the game evaluates the circuit on the ciphertext, obtains a resulting ciphertext, and sends that back to the adversary. Now, usually an evaluation of a circuit on ciphertext is publicly computable. So this additional evaluation oracle shouldn't give the adversary any additional power over the original NCPA game. So it's essentially here for completeness, because if already we're modeling a new security notion for FHE, we might as well include evaluations. But which is much more important, the adversary now also has access to a very restricted decryption oracle. So the adversary can pick a ciphertext from the state where MO is equal to M1. That is, the two underlying messages are the same. So from only the message, the adversary won't learn any additional information about the secret bit B. So it sends the ciphertext to the game, the ciphertext decrypts it, and then sends back the decryption of the ciphertext, which in the case of approximate homomorphic encryption is something of the form M plus E. Now, since MO is equal to M1, the adversary doesn't learn anything for the message, but it also obtains the noise, and it might learn something from the noise. So, but then the same way, we say that the adversary wins the q-IND-CPA-D game if in the end it guesses the secret bit correctly, and the scheme is said to be q-IND-CPA-D-Secure if over repeated iterations of this game, the adversary's probability of winning is only negligibly bigger than 1/2. Now, in the original paper, Li and Micciancio proposed this q-IND-CPA-D notion, but they left it as an open problem how to actually achieve it. Now, we know that this whole attack has been made possible because the approximate homomorphic encryption scheme during decryption returns us the randomness. So essentially to secure CKKS and to make it q-IND-CPA-D secure, we somehow need to hide this randomness, although it is being returned during decryption. And to hide this original randomness, essentially, there are two possible ways, which were already put forth in the original paper by Li and Micciancio. The first one is to add extra randomness to hide the original one, so to noise flood. And the second one is to go the same way as BGB and B3, that is to remove the randomness during decryption, which is what has then been called exact CKKS. The first technique has been addressed in a paper by Li, Micciancio, Schulz, and Sorel at Crypto 22, where they showed how much noise flooding noise is necessary to make a CKKS provably NCPA-D secure. It turned out that this was quite a big amount. Even though there is this big amount is necessary to achieve provable NCPA-D security, it might still be possible to get away with a less high amount of noise, but then which still will prevent the Li and Micciancio attack, but might not achieve provable q-IND-CPA-D security. But at any rate, adding additional noise, and especially a big amount of noise, takes a big toll on the efficiency of CKKS. Which is why in this paper, we investigate the second technique, which is to remove the randomness during decryption, but while at the same time trying to save most of the efficiency gains CKKS has. So what are our contributions? We define in the paper an exact version of CKKS. And we show how to round off the error to return an exact decryption result with high probability. And we show how to do this in particular without having a large impact on the efficiency of CKKS. So to do this, since we want to remove an error, we need to have a tight analysis of how this error grows. So we at first propose a tight analysis of the growth of the randomness in CKKS, and also as an additional tool, we present an estimator that allows to track this growth for any circuit, which might also be of additional practical relevance. And we use those results to prove that our version of CKKS provably achieves q-IND-CPA-D security. So what do we want to do? So if this is a CKKS message where we here have the bits that are untouched by the error, and here we have the message bits polluted by the error, essentially in an ideal world, what we would like to do is just to throw away the yellow part and just to keep the green part. And we can achieve this by scaling the message down so that all the error bits are pushed to the right side of the comma. And then by rounding it up to the nearest integer, this should only leave us with the green part of the message. And then if we return this message, there's no more error terms in it. So nothing that could be used in a Li and Micciancio type of attack. So this, in theory, should make CKKS q-IND-CPA-D-Secure. But in order to do this with good efficiency, we need tight bounds on the error so that we don't push too much of the green part onto the right side of the comma and round it off, but so that we essentially keep all the untouched bits and only round off the touched bits. So this is the first thing that we did in the paper. We propose a tight noise analysis for CKKS. And we do this by using average case noise analysis. Now, what is the problem with tight noise analysis? So as I showed in the animation at first, the original encryption randomness is changed when ciphertexts are multiplied, added, rotated. And if you have large circuits, like for example bootstrapping, where a lot of operations are used on a ciphertext, the behavior of the encryption randomness gets soon very complex, and to track it, not easy. So what we do in this work is we try to analyze the distribution of the randomness, and in particular the standard deviation, and then show how to combine those standard deviations into a standard deviation for large circuits, and how to use this to bound the noise. So in particular, we provide the standard deviation for all basic operations, show how to get tight bounds of that, and how to combine them into a larger circuit. So how do we obtain those bounds? So it can be shown if we assume independence that the distribution of the error can be quite well approximated by a normal distribution. And we know that the normal distribution, we can give the probability that a value that is normally distributed lies within a certain distance of a standard deviation from the mean. So we can use the standard deviation to bound the infinity norm of the error with high probability. So we calculate the standard deviation, error distribution, and then combine these. I won't show you in place because this leads to very beautiful formulas. So here we've got the standard deviation that we obtain for interpolating the Jth Chebyshev polynomial. If you're interested in these kind of things, I gladly recommend you to read the 40 pages of appendix of this paper, where we have much more of those beauties. But more importantly, these beautiful formulas lead to tight estimates. So, for example, here in the second experiment that we run was approximate sigmoid function, which is used in machine learning, by a Chebyshev interpolation, and then evaluate Chebyshev interpolation on ciphertext. So this is already a fairly complex circuit. We can do elements, then we can see here. We've got the standard deviation. This is the theoretical values that we obtain, and this is the practical values that we obtain if we just run experiments. So we see here up to 2 bits behind the comma, we are completely exact in our theoretical versus practical experiments. And if we then bound it, so here again, we've got the theoretical bound that comes out of the standard deviation. Here we've got the practical bound. So we see for the first parameter set, we have a deviation of 0.01. So that is 1%. For the second one, none at all. So the bounds that we obtain are very tight. And we then also build the estimator, which uses these theoretical estimations to give a true for the Latigo library. So essentially, this estimator, for which we will make the code public at any point soon, takes in the function that should be run on the circuits and then combines the theoretical estimates for the basic operations into that larger circuit, and it gives out an estimate of the noise for the largest function with no loss in tightness. So this estimator, which has been necessary for this particular paper, also we think has a practical relevancy in general, because it allows to get a very good idea of the development of the error, and therefore also of all the correctness issues involved for any circuit that one wants to evaluate before running the circuit and without having to combine by hand very large formulas. Okay, but further on now to exact CKKS. So we then moved on in this work to define R, or to define exact CKKS, or better, R exact CKKS. So what is R exact CKKS? It has the same key generation, encryption, and evaluation algorithms as normal CKKS, but it has a different decryption functionality. And essentially what the decryption functionality does, it returns all but the R's lowest bits of the message. So it just drops the R lowest ones and returns everything else correctly. We will always have to drop the R lowest ones because we can't completely remove the error, since this would break security. But at least like R exact CKKS is supposed to save us the green parts that I showed in the slide before. Now, this definition doesn't say us anything about how to achieve it. So this definition, in a sense, is the ideal functionality that we would like to have. However, as it always is, one cannot quite get the ideal functionality. So when we moved on to actually trying to show how does this decryption function have to look like so that we do just save the green parts of the message, we encountered some problems. The first problem led into us having to introduce this condition for delta correctability, which already was introduced in a paper on the precision loss of approximate homomorphic encryption, which dealt with the same problem. So here again, we need a similar condition of correctability, which essentially says we need to guarantee that if we multiply our message by 1 over delta, we end up onto an integer. Because if we don't have this condition, then essentially we can predict how big the noise gets. But if we don't have this condition, then we get an additional rounding error from the message, which we cannot at all predict. And then we have no chance of more or less determining where the message will round to. So to give you an example, even if we only have a very small error, rounding may change all the bits in a ciphertext when the error is rounded off. So for example, if we have the value 0.99999, this is really close to the nearest integer, but if we round it to the nearest integer, then each and every of the message bits will be changed. Now, if you look back at the problem that we wanted, so that we have the green parts of the message, and through rounding, we just want to get rid of the yellow ones. If anything quite like this happens, then we will just round off all the message, or then we won't return a single correct bit because all the bits in a message will be changed. So this is why we need this condition for delta correctability to avoid this problem. But this also is a problem in other schemes like Kyber, so this is not new to CKKS. So then we defined delta R exact CKKS, which essentially what we do in CKKS, we have in delta R exact CKKS, we have the same key generation, encryption, and evaluation algorithms as in CKKS, but we do have a different decryption functionality. Now, how does this decryption functionality work? We here scale down the message by some scaling factor. So essentially, we try to push all the error to the right side of the comma. The scaling factor is determined by bounds on the noise that we calculate from the standard deviation, as can be seen from the first and second line of the definition. Then we round the whole thing. So now we cut off all the bits that are on the right side of the comma. And then we just scale the whole thing back to its original size so that we're only left with the green message bits. Now, in the ideal functionality, we only called it R exact CKKS. Now here it's called delta R exact CKKS. And this is because the bounds that we're calculating to know by how much we need to push our message to the right side of the comma are probabilistic. Therefore, they might fail. And delta is the probability of the noise bound holding, therefore 1 minus delta probability of the noise bound failing. So in contrast to the ideal functionality of R exact CKKS that we would like to obtain, we have two minor things that we need to concede. The first thing is we only achieve it with high probability. And the second thing is we need this condition of delta correctability. And so all of this then essentially leads to this theorem where we show how we can bound the advantage against q-IND-CPA-D security for our delta R exact CKKS scheme. And we can see we have here 1 minus delta to the q. So this is the probability of the noise bounds failing after q calls to the decryption oracle, plus the advantage against the IND-CPA gain. So if CKKS already is IND-CPA secure, and we can make 1 minus delta to the q negligibly small, then indeed we achieve provable q-IND-CPA-D security. So we prove this by a game-based proof through which I just would like to very quickly walk you. So we have 4 games where GO is just the IND-CPA gain. And in game 3, we have an encryption oracle, which is the normal encryption oracle from IND-CPA-D security with the minor addition that we are also calculating the standard deviation of a fresh encryption and are adding into the state. But since this can be publicly computed, this encryption oracle has no difference in security from a normal encryption oracle. We also have an evaluation oracle, which again is the same as the IND-CPA-D evaluation oracle, just we also here compute an estimate of the noise and add it to the state. The real work happens in the decryption oracle, where we first check that the two messages are equal. Then we compute a bound on the noise. From this, we determine our rounding factor. And then if the bound on a noise holds, we return just the decryption of the message. If the bound doesn't hold, we still return the decryption of the message, but we set some flag bat to true, which is then important for analyzing the probabilities. Then in our second game, we essentially again calculate the bound of the noise and the rounding factor. We check whether the bounds hold, but then just return the ideal functionality. So we just return the B minus R topmost bits of the message. So essentially here now, if the bounds hold or not doesn't really matter, because it doesn't matter to the ideal functionality. And again, if the bounds don't hold, we still do the same thing, but we set a flag bat to true. And then we quickly see, I said, okay, so if the bounds hold, then delta R exact CKKS is the ideal functionality. Therefore, those two games return the same thing. If the bounds don't hold, then there is a difference between those two games. So the difference and advantage between those two games is just the probability that the bounds don't hold. Then in game G1, we still calculate by how much we need to shift it, but we don't bother with decryption anymore at all. And we just simulate the decryption oracle by just rounding off the 1 over delta last bits of the message itself. So since the ideal functionality returns pretty much the same thing, there is no difference in advantage between those two games. And then the game GO is just the NCPA oracle at all. So there's also no difference in advantage between the games G1 and GO, but the probability that the game GO is won is the same as the probability that the NCPA, precisely in the hop between the games G4 and G3, we get the probability that the bounds fail. In the last hop, we get the probability that the NCPA game is won, and this is how we obtain the theory. Now we are left with some open questions, out of which the biggest one is to investigate this condition of correctability. So in particular, how large is the class of correctable circuits? Can any circuit be made correctable? If so, at what costs? Or is it possible to make the proof go through without the condition of correctability? And thereby I reach the end of this talk, and thank you for your attention. And do you have any questions?